Good morning, everyone. I'm very happy to introduce our second speaker, Professor Antonio Acin, a leading figure in quantum information science. Professor Acin earned his PhD in theoretical physics in 2001. Then, following a postdoc in the University of Geneva, he joined ICFO in Barcelona in 2003, where he is currently leading the quantum information theory group, focusing on quantum entanglement, non-locality, and quantum cryptography. His pioneering work in device-independent QKD has significantly advanced the field, and Professor Acin's contributions have been recognized with multiple European Research Council grants, including the Access Chair in Quantum Information Science in 2016. Acin has served on the scientific advisory board of several research institutes in Singapore, Vienna, and Natal. In 2021, he published his own book, Einstein and Intuition, and up to now, he contributed to more than 180 peer-reviewed scientific publications. Please welcome my great Professor Antonio Acin.
Thank you very much for the introduction. I was surprised that you made a reference to the book. One day I will tell you the story about this book with a glass of wine. And you can even find it in Italian, so if you are interested. Yeah, it's a pleasure to be here also because I have Italian genes and actually from Venice, close to here. I mean, one day I hope I will be able to go talk in Italian, but I'm not going to do it today. Yes, also nice to talk to you. So it's a very quite high-level talk. So it's not talk about my research. It's more talk about perhaps my most favorite result in quantum physics, which is by the Bell theorem. And then I will also give you a quick overview about my field, which is quantum information science and technology. So okay, here's I will start by a bit of history about the Bell theorem. Okay, so let me ask you those who knows about Bell theorem here? Okay, well, let's see how it goes. I hope you learned from my talk anyway. So this is a theorem that actually one of my points that the theorem has not much to do with or the result that the theorem relies on, which is what is called the inequality. You will see it has nothing to do with quantum physics. Because basically, what the theorem solves is the question of whether some natural classical models can give the same relations as quantum physics. Okay, so this was the theorem solves, and it was some sort of answer to a question that was posed in 1935 by Einstein, Podolsky, and Rosen, and this was a question that had some impact in not beyond the scientific community, because Einstein was like a rock star at that time, so he was a very known scientist, but he was also known beyond science. And there was this article that I believe was going to appear in Physical Review, not even published, but then the New York Times already was commenting on that. And well, you may know that journalists, well, I hope none of your relatives is journalists, but journalists usually, they tend to exaggerate the claims, okay? And what they wrote in the journal was that Einstein was, I mean, it's nice also because the article is by 3 people, but they don't care about the other 2, okay? The people lecture about Einstein, okay, it makes sort of sense, but you have to be a bit more polite. And they said attacks quantum theory, okay? So this is the headline. Well, then, if you read later, well, they say scientists and 2 colleagues as if they were not scientists, okay? And then, but then they explain a bit more, okay? They find that it's not complete even though correct, okay? And this is much closer to reality, because what the article says, the Einstein-Podolsky-Rosen article, what they say at the end, is that, okay, they say that it's shown that it does not provide a complete description of physical reality, okay? And, but okay, and what they want there is to find a complete description of reality. Okay? This is what they want. It's also like an indication to the community, like, okay, we are showing some indication of quantum theory, and we believe that it's not complete. And okay, I hope nothing happens. And then they invited the community to find a complete description of reality according to what they found should be physical theory. Okay, so this was the invitation. So what happens usually is that we physicists, we are crazy people, but not, I mean, we are practical. So you have a theory that describes reality, you don't look for another one, okay? Unless you are a super deep thinker like Einstein and colleagues. So you're happy, you have a tool that works. Usually, I mean, maybe during the weekends, you spend some time thinking about other theories, but you don't desperately look for the other theories. Okay? So as you'll see, some people thought about this invitation by Einstein, Podolsky, and Rosen, but it's not that all the community started working on that because there was no need for that. So what was the problem, and what does it make more complete theory? Okay. So I would say that basically the problem with the EPR, so Einstein, Podolsky, and Rosen, so I'm going to refer to them as EPR. Okay, the problem EPR had was mostly with entanglement. Okay, so this is a phenomenon that appears in quantum physics, that appears between two quantum particles that can be in a state. And okay, the standard explanation that people give about entanglement when you have a general talk is like you can see this as two dice. And it happens that I have one die and Alberto has another one, and then we are at a distance. And when I measure the die, I see a result that can be 1, 2, 3, 4, 5, 6. So it's random, it looks random to me. But it happens that whenever I get a 3, he gets a 3. Whenever I get a 4, he gets a 4, and so on. Okay, so this is a bit. Okay, so maybe he didn't like it, he doesn't look very happy here because there is an action at distance. So the results are locally random. I see 1, 2, 3, 4, 5, 6. I cannot predict what I'm going to get. The theory does not allow you to predict what you're going to get. But at the very same time, there is an agreement of very large distances. Okay, so these two things are a bit complicated. I would say action at distance. I'm not sure what's more discomforting for Einstein, but I'm going to focus a little about the fact that things are random. Because I think this is, in my opinion, this is what he meant. He and colleagues meant when they were saying that the theory was not complete. Okay, so this is a very standard explanation about entanglement and why people didn't like this. But there is also something that Reinhard Werner and Michael Wolf introduced in I think it was sort of general public paper or high-level paper, that they call the ping-pong ball test. Okay, probably you have never heard of this concept, but I think it's very good for what I'm going to say. And basically it says that if people give you an explanation about a quantum effect, and you can explain the same thing with ping pong balls, this is not an explanation for a quantum effect. Okay? So what is the explanation about this quantum dice that I was using? It's like, okay, you get a particle, you measure the particle, you see 1, 2, 3, 4, 5, 6, so you cannot predict what you're going to get. But once you see the number you get, you can predict what the other party has. Okay, this is not an explanation about entanglement. Okay, so now I'm going to give you another explanation, okay? About something similar. You have there is a referee or someone who puts 2 ping pong balls in 2 boxes, and they can be either 2 blue or 2 red. But we, Alberto and I, we don't know which balls we are going to get, okay? Which color we are going to get, okay? So they are sent to us. I open the box where the ball is, and then I see that it's blue. I cannot predict in advance whether it's going to be blue or red, so it looks random to me. But when I open the box and I see blue, I know that he's going to get blue, and when I see red, I know that he's going to get red. Okay, so there is local randomness and agreement at distance, but this cannot be entanglement after all, or what discomforted Einstein. So what is the problem somehow in this explanation? Why was at the very end the difference between these two explanations? In the narrative I'm telling you with the ping pong balls, the color of the ping pong balls the colors are defined when leaving the source. Okay, so it is true that for me I don't know it, but in my narrative I say that the color is defined, and the color comes with a properly defined color that my explanation simply reveals. So the randomness that I see is just a matter of my ignorance, because I cannot predict in advance what is the definite color that the ping pong ball has inside the box. But this does not happen with entanglement in quantum theory. Okay, the narrative of the theory doesn't tell you what is the result of the speed measurement you're going to implement. Okay, so this is a problem. The theory is not complete because I cannot explain with my theory, I cannot give an explanation to the experiment as the spin is defined and my measurement simply reveals a quantity that was existing. Okay, I hope this is clear because it makes a lot of difference. So in the ping pong ball test, the randomness is simply a matter of your ignorance when you open the box because the color is well defined. In the quantum explanation, this randomness is intrinsic to the theory. It's not a matter of ignorance. Okay, I believe this is the problem. Okay, so this is what I want to tell you here. In the ping pong ball test explanation, things are defined. In quantum theory, things are not defined. And Einstein, Podolsky, Rosen hoped and believed that that was simply a limitation of the theory. And there was another theory that was explaining an entanglement experiment with defined properties. as I explained the ping pong ball experiment with defined properties. This is why they were saying, look, guys, we have to find a better theory, maybe with the same predictive power as quantum physics, but in which the narrative is closer to this ping pong ball test, in which properties are defined, and your measurement simply reveals something that your ignorance didn't know, but it's not because things were intrinsically random. Hope this is clear because it's very important, the message of my talk. Okay, and there is this famous quote by Einstein, he does not play dice. Okay, this is what he didn't like it, the fact that it's not that things are intrinsically random in theory, but about randomness is a matter of ignorance about well-defined properties. Okay, so this is what they were suggesting, that quantum physics was an incomplete theory, and then there should be a better theory in which you have this narrative ping pong balls, okay, in which things are defined and your measurements simply relate properties that exist, which is not the case in quantum physics, okay, because string is not defined until the moment you measure. Okay, so they were telling about some properties of locality and realism. Okay, and then I must say I'm not a big fan of this terminology. Okay, I will tell you why. But say Bell theorem, what it proves is that this idea of finding a complete theory, a more complete theory, making the same prediction as quantum physics in the EPR formalist is not possible. Okay, so basically this is what Bell theorem tells. I'm going a bit fast here, and the experimental demonstration of the theorem proved that this was impossible. So why am I going a bit fast here? Because this is not a talk about history of physics, so I'm not going to follow the historical perspective. This is a talk on how we understand Bell's theorem today. Okay, well, if you want more exact, my understanding. Okay, maybe you may have some other understandings. I'm going to tell you my understanding of Bell's theorem, in which never use locality or realism. This is something a bit complicated with realism. I don't especially like these things. Okay. So this was a bit of history to introduce the topic. So now let's say forget about this. Now I'm going to give you my explanation of Bell's theorem. Okay. I mean, please remember what was in my opinion, what Einstein and Rosen were trying to achieve. Okay, they were to explain entanglement at ping pong balls. Okay, so like with defined properties that you mentioned already, but they exist before the measurement well defined. Okay, so there is a concept that is very important what I'm going to say, which is two concepts, correlations and causality. So I think it can be said not only in physics, but in any discipline, the question, or say one of the main questions we want to solve is we observe correlations. So we make experiments and we observe some data that are correlated, and we try to explain the causes that could explain this data. Okay, this is in physics, like if I perform an action here and I observe an effect, what is the probability that I see something when I perform another action in another space in instance, have another event in space-time, okay? What is the probability that how the probability I observe here is affected by things that happen in another position in space and time, okay? And usually we can just explain whether things can influence or not, okay? But relativity was invented to explore causality, no? In physics. But I don't know, I mean, in medicine, if you want to know if I take a pill, what is the probability that sickness disappears, or there are many things we try to observe correlations, and you tend to attribute causes to these correlations. Because you want to explain correlations through causes. Okay, so what is the language that we use for that? Okay, and for instance, we observe correlations between two effects, like in this example A and B. Well, let's assume you make an experiment and you observe people who have lung cancer and who smoke, and you observe some correlation between these two things. Okay, so you will tend to say, okay, if you smoke, you have cancer. But in principle, you can always say, sorry. Okay. You can also say, I mean, it's a bit stupid. If you have cancer, you tend to smoke. Okay, this is compatible with your correlations. Okay, it's a bit too much maybe for our common sense. But then, for example, the tobacco companies, they can tell you, no, there is a variable you didn't include in your study, which is people are sometimes they have more tendency to be nervous, and these people tend to smoke and tend to develop cancer, and this explains correlations. It's possible, okay, and maybe not so crazy as if you have cancer, you smoke, okay. Okay, what I'm representing here is that this is the language we use, and what we do is like we have some variables that we observe, who smokes and who has cancer. You may believe that in your study there are some variables that unfortunately you cannot observe, but they might be relevant for the problem, people who tend to be nervous, and then you put, so we represent these variables with circles if you can observe, squares if you cannot observe. They are sometimes called latent or hidden variables. And these are the observed variables, and we put arrows. This is a language people use to describe causality. This is called directed acyclic graphs. It doesn't matter. It's very intuitive to understand what I'm showing you. Okay. And I think it's a very natural language to represent physical experiments at a very high level. Okay. So if you have this experiment, you go to the lab and you prepare some particles here, and these particles go to a central location in which you observe them. Okay. So you may have different preparations. So you have buttons to prepare different particles. This is a high level. Okay. It's some sort of theory-independent language. There is a theory in which I prepare a particle that goes to a central location, and I may vary the preparation of this particle by pressing a button. And then I make an observation of these two particles, and I get R possible results. Okay, I'm not saying this can be classical physics, quantum physics, any crazy physics you can invent. Okay, I'm just saying that there's an experiment in which some systems are prepared and measured. Okay, so you represent this by there is an effect here, which is my choice. Another effect here, and what I observe here depends on my choice here and there. Okay, just attributing causes, looking at the experiment, I can attribute the causal connections in the experiment. It's very easy to make this analogy, right? Okay, so the important thing that we understand now is that when you make these drawings, when you explain your experiment through causes, you put these arrows, you have constraints of the probability you can observe in the experiment. Okay, this is very important. You should remember this is one of my take-home messages. Okay, when you say how things behave, the narrative of your experiment tells you constraints about what you're going to see in the experiment. So for instance, let me see this. Okay, so I have something that happens here, here, and there, and this goes here, and there is something that you don't see and it comes here. Okay, I'm inventing. You can represent many causes now with these pictures. Okay, so what you can see here is that if you estimate the probability that Alice and Bob see it, which means, okay, here you have all these observed variables, and this is latent. Okay, remember, you only see the circles, you don't see the squares. So you see the probability that this A, B, X, Y, C, okay, I have to sum over these objects here. Since there is no arrow going from here there, the probability these people see should be independent of these variables here. Okay, this simply follows from the arrows. Okay, if there was no arrow, there is no cause going from here to there. What these people see, marginally, the marginal probability should not depend on what these people do. Okay, this is just follows from the causes. And you have more constraints. I mean, sometimes it's not easy to identify these constraints, but you have a series of constraints that follow simply by the arrows you decide to put in experiment. So what is the best scenario then? The best scenario is some sort of causal model in which what do you do in a Bell experiment? For those who know, you prepare this entangled state or this ping pong ball test. Someone prepares from a source. They go to Alberto and to me, and we perform actions on these boxes. Okay, that we get that can have entangled particles or ping pong balls or whatever. They have something. We perform actions on these systems that came from the source, and we see results. Okay, so this is the way I represent more a la physics, black box picture. Okay, so we perform actions and we see results. So this is a Bell test, and here I'm not saying anything about quantum classical physics. I'm just describing a very high level description of the Bell experiment. Okay, things are prepared, they propagate in space-time if you want. They are divided into different places, and we perform actions here. And we assume that what I do here does not influence what happens there because we are at this time. Okay, so this is why I don't put any arrow. There are no things going from one place to the other. Okay, so what is the causal model for this experiment? I don't see what the source does. They gave me this. I'm ignorant. I decide to perform an action and I get an output. The observed variables are X and A, Y and B. I don't know. I indirectly observe the source by making this choice of action on the particle that came. Because this is the causal model associated to this black box experiment. Okay, this is not classical quantum physics. Okay, it could be also a crazy supra quantum theory. I would still be using these things, explaining how things happen in, say, causally. I can also say, okay, I want to enforce these causality corrections, and then my experiment will have to look like this, okay? So I will have to ensure that this particle goes there, and this particle goes there, and what happens here does not influence. So you will arrange your experiment to try to enforce these causality conditions, okay? But this is a possibility of doing. Okay, so what are the models that make sense in this picture? And what are these complete models, these ping pong ball type models? The narrative, we want to describe what happens in my experiment, in this count description, in a deterministic way. This is why we use Theorem, okay? So if I get a system, I will say, okay, the system has some instructions, like a program, and the system gets the inputs and produces an output. Okay, so for instance, here, if you take this causal thing, okay, you have these inputs, and A and B and C are produced in a deterministic way from what they got, okay, from X and lambda. If this, I don't know, I mean, I hope you understand the mathematics is very easy, yeah? So I don't have access to these things, so this is why I integrate, and A, B, and C are deterministic functions, the outputs are deterministic functions of the inputs. This is common sense, okay? So here is A, if X is equal to 3 and lambda is equal to 4, A is equal to 7. Okay, there is a recipe that tells you how to produce the output given the input. There is a program, if you want, if blah blah, produce blah blah. To me, this is common sense applied to an experiment. So what is Bell inequalities? Okay, then you apply these deterministic models for this, remember, this is the Bell test. Let's apply this deterministic explanation. So what this guy produces is a deterministic function of X and lambda, and what this guy produces is a deterministic function of Y and lambda. I don't have access to lambda, this is why I sum over lambda. It happens that the probabilities you can see in this experiment under these constraints satisfy some conditions. These are Bell inequalities. Okay, so you can see that, as I was telling you, causality and this determinism assumption. So outputs are produced according to your causal conditions in a deterministic way, and it happens that these probabilities satisfy some constraints that you can write as a form of inequalities that have this form. Okay, again, there's nothing quantum in what I'm saying. Okay, it's just causality followed by determinism. So it has nothing to do with quantum physics because it happens that do you know who Boole was, the inventor of Boole algebra? Have you heard of Boole algebra? Okay, this was invented by George Boole. Okay, this guy was dead before the advent of quantum physics. He had Bell inequalities in his papers without knowing about quantum physics, because it makes a lot of sense, right? You want to understand how devices behave at distance, and you apply common sense. Well, they will behave, they will produce outputs in a deterministic way depending on the inputs, and you try to understand what are the correlations you can get with that. Okay, you don't need to think quantumly to formalize this, and he was doing this before quantum physics. Okay, so let me see what this happens with the experiment that you may know. That's very simple. Okay, so standard Bell test. So the source prepares, particle goes here, particle goes here, and now you're going to make two experiments, two measurements, getting two outputs. Okay, but again, this is like you give a bit or you press a button, you do something on the device, and the device gives you a back result. And I'm going to label the result plus and minus 1. This is conventional, but it's useful for my presentation. Okay. And then I'm going to take this quantity, A1, B1 plus 1 is a weird quantity, but why not? So A1 is the output of this box when you use input 1. So it can be a plus and minus 1. And B1 is the output of this box when you use input 1. And B2 is the output of this box when you use input 2. I hope you understand the notation very simple. Okay, let's try to use our common sense to understand how much this quantity can be. Okay, so in classical physics, in complete models, in ping pong ball Bell test, even if I know what the source produces, the output is going to be plus or minus 1. Okay, so in our standard common sense, in the source, you have produced a program, and the program says if X equal to 1, A is equal to plus 1. Or if X equal to 2, A is equal to minus 1. Okay, You can even think that there is a small demon sitting on the box, okay, with this piece of paper, and then the demon says, x equal to 1, he reads, then output is equal to 2, 2 plus, and he does it. Or a problem, so to say. Okay, so under this common sense assumption, I would say, what is the value of this quantity? Okay, you can see, for example, let's have a situation in which the devices give +1 no matter what. Is a possibility. Okay, so this is +1 and this is +1. +1 times +1 is equal to +1. Plus +1 times +1 is equal to 2. Plus +1 times +1 is equal to 3. Minus +1 times +1 is equal to -1. So in total is 2. We all agree with this, right? It's very simple. I mean, we do more complex calculations in my group. I can tell you. Okay, so these two. Okay, you can see that for all possible plus and minus assignments, this quantity is either 2 or -2. So even if this varies with time, the expectation value that of this quantity is going to be always bounded by the maximum, which is 2. I mean, this is really common sense. Okay, so I'm sure we leave this room, we go to the streets. We explain this to people with a very simple education in mathematics. I'm sure these people will be willing to bet money that this quantity will never be larger than 2. Okay? Because it's +1 times +1 plus, okay, it's very simple mathematics. Okay, so now I didn't use quantum physics, now we use quantum physics. Because the amazing thing is that this bound can be violated in a quantum experiment. Okay, so if you are not surprised by the result, my talk is a failure. It's amazing. Okay, so yes. So what I'm saying by this is that if a source prepares a particle and this particle goes here, and now it's the same, you know, see, it's the same explanation, the same causality connection. Okay, there's a source, but now the nature of the particle coming from the source to the devices is just quantum. And then you make this measurement and you get the outputs, and you prepare this source in this state and you make these measurements. Then you can see that the CHSA value on average is larger than 2. Okay. I always say when I did this talk, I mean, if we could do this, I mean, we could now go to what is the most, I don't know, the most popular street in Padova where people go. In Barcelona, we have La Ramblas. I don't know if you have been to Barcelona, because many people go there. So you make a small stand and you explain to people these rules of the game. You say, okay, I'm going to send 2 people to 2 places. I'm going to ask 1 and 2. They have to say +1 and -1. We need to put money that we are going to get values larger than 2. We will get people putting money. Okay? And what you have to do, you have to prepare. Okay, we cannot do this now, okay? But someday this will be possible, okay? So Alberto and I, we have to have this entire state in our pocket quantum memory. When we get the input, we take the quantum particle, we measure, we see the result, and depending on the result, we provide the output. And these people, we magically see that this number is larger than 2. Okay, so this is unfortunately not possible. It can be the first real application of quantum technologies, okay? So the one producing a lot of money for you. Because I'm sure you will see people betting on that. Okay, so I think it's surprising. And what this is telling you is that this bound is something that the theories by Einstein, the ping pong ball theories, predict, okay? Because your measurement only reveals a property that exists. Okay? The +1 and -1 is already defined what the particle arrives to you. It's not your measurement that reveals that creates this output. Okay, it's already there in the box. So this is proving that on this idea of Einstein-Podolsky-Rosen of having a theory beyond quantum physics that is more complete than quantum physics is simply impossible, because this theory is violated by inequalities, and the inequalities are violated in experiments. So what this is telling you is that, well, he plays that. Okay, so you have to abandon theories. Okay, there is in which quantities are well defined, and the theories in which my measurement simply reveals theories and quantities that are well defined in the theory. Okay, so we have to abandon this. Okay, there is another explanation which says that you believe that these causal connections are not satisfied by your experiment. Okay, this is also a possibility. Okay, you believe that no, actually you believe that things are behaving according to that, but there is an arrow coming from here to there. Then this bound is no longer valid. Okay, so this is a possibility. In my opinion, there are ways of enforcing these causal constraints in an experiment, and then divide the inequalities, and you have to accept that there is some interesting randomness in the field. Okay, so this is what Bell theorem is. It's also interesting from the point of view of causality, because this is telling you that you may have situations in which the same experiment cannot be explained by these causal connections in classical physics, okay? But it can be explained by the same causal connections when you replace classical causes by quantum causes. I mean, causes mediated by quantum particles. I think this is relevant. I mean, there are books on causality, not written by physicists, usually written by statisticians. So they are this thick, okay? Because causal networks are used in many fields, okay? But this implies that at some point, I believe, they will have to write an appendix about how everything changes under the pressure of quantum information. Okay? Because if you want, you can also say that this is a causal inequality for classical causes, but this is no longer a causal inequality for quantum causes. It's the same causal diagram. I only change the nature of the variables, bringing the causes. Okay? Okay, so the nice thing is that, well, this is all theory, but of course the most relevant thing, well, apart from, no, everything is relevant. So also relevant that the inequality have been violated by experiments using photons. Okay, there was experiments. And this is because the photon is the best particles we have to send information to two different devices. And well, another prize visit was given, say, to the people doing this first experiment. There was first Clauser. Okay, this was a huge experiment, and then Aspen with Dalibard, Roger, and Ranger. Okay, also again a huge experiment. And okay, and they violated this the inequality is proving that well, this dream of Einstein-Podolsky Rosen was no longer possible. Okay, so this is what I said. You are not surprised it's a failure. Maybe you need a result, but I still hope that you enjoy the explanation. It's clear the situation in which quantum physics really departs from classical physics. Okay, here is something that you really cannot explain in classical physics. So it has been confirmed. And now the question is whether we can use this new theory that has no analog in classical physics to do something relevant. Okay. How much time do I have? 5 minutes? Okay, this will be super fast. Well, yes, and this is what we do in my group, okay? So we do quantum information theory. So basically what we try to do is we want to understand what happens when you encode information on quantum particles, okay? And this is happening because we now have the technology, we can put bits on quantum particles. And this transition is, physicists, they have made this transition, well, physicists too, okay? So we have made, they have made, physicists made this transition many years ago. Quantum physics was invented to explain this transition because people realized that what happens here, you need a new theory, and no longer Newtonian physics no longer valid to explain what happens for microscopic phenomena. Okay, this was many years ago. So now we are doing the same transition for information devices. And also another take-home message, important message from my talk. I find really remarkable that the things you can do when you encode information on quantum particles are different from the things you can do when you encode information on classical particles. So I believe this is an engineering department. I also have a double degree in engineering and physics. So if you had asked me at that time whether I thought that by encoding information on quantum particles, this would have made a difference about what you can do with information, at that time, I would have said no. Because in my understanding, one of the nice things of information theory is that physics is irrelevant for information theory. In my understanding, I can do a bit with this object, this can be 0, this can be 1, and this is as good as any other physical representation of a bit. Not practically, we don't send these things at distance, but logically, this is as good as any other bit. This was my understanding. I didn't take any course on information theory while studying physics. Okay, all my course on information theory was on engineering. So if you had asked me this question at that time, I would have said, no, I don't see the point. Physics is irrelevant for information theory. You would do the same because a bit is a bit no matter how you implement it. But I was totally wrong. Okay? Because the theory takes difference, because physics matters for information processing. So the thing you can do with some devices are not the same if they are classical or quantum devices. Maybe you already have integrated this message. For me, it was a surprise. Okay, so let's do that. Let's put a bit on a quantum particle. Okay, I only need something like this. Okay, I only need a system that can take two values, and I will call 0 and 1. So for instance, I can use a particle, and I can put in two different positions, and I will call one position 0, and the other position I will call 1. Now you open a textbook on quantum physics, you don't have to go to page 135 in some textbook of quantum physics. The postulates appear at the very beginning. And you don't have to go to the nth postulate, you read the first postulate of quantum physics. The first postulate of quantum physics tells you a quantum system is described by a Hilbert space, a vector space. So this means that if you have 0 and 1, because of vector spaces, you can have any linear combination of 0 and 1. This is first postulate of quantum physics when you encode a bit on a quantum particle. So a quantum bit is richer and different from a classical bit because they can be in superpositions. It's something, again, very simple, but very deep. Okay? So potentially you have something richer, potentially you can do new things, but this is what the field is about. Okay? So I'm always ambitious when preparing a talk. I was planning to tell you things about what you can do with qubits. I'm afraid there is no time, but basically, I will give some super ultra fast summary of what I was planning to say. So this is why now my field and people want to understand what you can do with qubits, because we understand that qubits are different, and we understand that there is no explanation of these effects in classical physics, because in particular we violate the theorem. So we have a new theory in which you have new units of information. You have to understand how to use them. So there are quantum computers, quantum cryptography, quantum sensing. So there are now efforts, in particular in Europe, there is this flagship on quantum technologies, and the effort has been structured on 4 lines, okay, which are given here. So this is the new picture people are using. I'm more a vintage old person. I prefer the old one, okay, so for my talks. You see, it's less nice. It's more fancy, but okay, for my talks, I use this one. So usually they are represented by these 4 vertical pillars. And you have some things that are transferred to these pillars, like engineering, control, software theory, there's also education, and so on. And while these things try to understand how to use qubits, quantum bits for communication, computation, simulation, sensing, and metrology. But I believe I don't have time to tell you about these things, or maybe just very quickly. So what is sensing? You want to use quantum bits to measure relevant quantities with an advantage. Okay, so this is what you try to do. So that I will use these qubits to sense, to measure particles, to measure effects. That's what we want to do in metrology. Computation and simulation. You see, I'm very optimistic. But I don't have time to tell you all these things. It's very interesting, but I don't have time. So what is the main goal? We want to use qubits to solve computational problems that are of relevance. Okay. Okay, here maybe I want to spend some time. There are many articles where people are telling you, now we use a quantum computer for a quantum advantage, and things like this on the headlines. This has not happened yet. Okay, so now you give me a quantum computer, I wouldn't know what to do with it. Okay, so we don't have, with the present computers we have, we cannot solve a problem better than our classical computers. This has not happened. Okay, I'm sure you will get new articles in the press or saying new demonstration of quantum advantage. Read everything, okay, because so far this hasn't happened. Then quantum communication, we can have, say, the main goal is to have a grid of connected quantum devices that sometimes people call quantum internet. So basically what we try to do is the same as we have today, computers, internet, sensing devices, but now you put quantum in front of it because you do it with qubits and you try to do these applications better thanks to quantum effects. Because you can have to remain the same or maybe better. Last thing, and this is important for me, is not only, I'm sorry for you are engineers, it's not only a matter of engineering, okay? So there is still a lot of basic science that is relevant to advanced physics. Okay, so it's nice because now we are in this intermediate stage in which we need a lot of engineering, but still fundamental science is needed. Basically, everyone is needed. Let's say this is nice about the field. Okay, so I conclude now. In my talk, I was the way the talk evolved was like this. Okay, so I started with foundations. I like quantum foundations. I like a lot, as you probably could see, the theorem. So I started with quantum foundations, telling you the result in which you can really see the difference between classical and quantum physics. And then I used that to motivate the quantum information science, the idea that you can do different things when you have quantum bits. And I ended up with quantum information technologies. Okay, this transfer has happened. Okay, we have already gone this transition. And now we are in the moment in which there is communication in all directions. Okay, so again, we still need fundamental concepts, but we are also here in which we need a lot of technologies to develop these things. But so there is a fluent discussion about these three ideas. Okay, so it's a very exciting moment for you young people. We can do a PhD, and after the PhD, you can go into a postdoc or go into a quantum industry. There are many possibilities there for you to work. Okay, thank you very much for your attention.
Any questions?
It's more like a curiosity. Where do you think this obsession with determinism comes from? Why the obsession? Including Einstein and people of his time. Like, why do we like determinism so much? I would say now that we got a little bit more used to this quantum, it's like we don't rely on determinism as much as they used to.
Well, I don't know.
It's a cultural thing.
Well, for sure, yes, no, but it's hard to accept that. I mean, we do that. Okay, so it's hard to accept that things don't behave according to some pre-established. At least for me, I understand some people. It's a matter of convenience, okay, of the subjective decision. We are faced, it's a pity that Einstein didn't see Bell's theorem, okay, but when you arrive to Bell's theorem, as you know, the fact that these two events that happen at Alice and Bob are not causally connected, a way of enforcing that is through space-like considerations. That is, we use relativity. So Einstein, when see a Bell experiment, he needs to choose between either determinism or the failure of causality, okay, of relativity, if you want. I think the two things are, at least in my brain, they're quite, I mean, it's deeply into that. I mean, now I'm already got used to think about non-determinism, yes, randomness. But I think it's really very mostly a cultural thing. So we used to think, people used to think at the time that things were deterministically defined, the future was deterministically defined by the past, okay? And of course, by the relevant quantities in the past, what causally influences the future, okay? So I think it would be nice if something didn't happen, that Einstein at the time, he would have needed to choose between his theory, relativity, or determinism, okay? So we didn't know what he would have chosen, okay? In our case, most of the community chooses to abandon determinism, okay? Because we tend to think that causality is so deeply into science, and we accept, okay, for sure I can design experiments in which what I do here does not depend on what happens there, no? If we are all connected, this sounds like a bit, but there are theories in which people, like bomb theory, in which people, they remain deterministic, and they violate causality. Okay? So it's a matter of choice. I mean, we cannot falsify these two things.
I remember you said that in regards to the computation with advantage, that it's not something that is going to happen or has happened yet.
No, it's going to happen.
It will happen.
I hope it will, yes.
Is it just a matter of time, or are we like, are we in need of some big breakthrough?
Okay, so it's very hard to make predictions. Okay, it may happen for Shor's algorithm, which is an algorithm that people invented to factorize large numbers. It sounds like a very academic problem, but if you know, you can hack cryptography with this algorithm. But for that, you will need a lot of time. Okay, so because you need a lot of qubits, and we don't have them. So I think at the moment, the advantage is also coming from the fact that we don't have beyond Shor's. I'm not sure we have really many practical situations. Okay, even practical what it means, but yeah, like scientific problems in which, or no, practical problems in which the current or near-term quantum devices can provide an advantage. Okay, probably the first quantum advantage will go in the simulation of systems. Okay, so this sounds a bit maybe for layman people it sounds like, oh, why? But if you go to supercomputers, a lot of times it's devoted to simulate systems of scientific interest, okay? I mean, for medicine, biology, physics, or whatever. So when in quantum physics, our simulations are hard because we don't have qubits, and we have qubits under control. We will have the possibility of simulating this system of interest, and this can be an advantage because we may be able to improve the design of materials. Okay, this is standard introduction of papers, okay, but I think the possible advantage will come more on the field of simulation in the short term. But we add also theory. Yes, I think everything is needed. Yes, coming back to this message.
So earlier you mentioned quantum networks. So I was wondering, I mean, considering all the developments in QKD and quantum communication, if you think that the time scale to have like a noise resilient, large scale quantum communication networks is like shorter than having like fault tolerant quantum computation.
Yeah, okay. It's also a difficult question. I think it's also there are barriers there for long distance, really long distance. So what are the solutions? Direct transmission, if I want to send you a qubit, this works for say few hundreds of kilometers. Okay, when we go to much longer distances, I have to use either satellites, but then you have to pay a lot, or if you know quantum repeaters. I have already some seniority. When I was postdoc in Geneva in 2003, they had a project that was called quantum repeater or something like this. And one of the deliverables was proof of principle demonstration of a quantum repeater. That was 2003. I haven't seen any proof of principle of quantum repeater. Okay, or maybe that isn't really. So I think it's also challenging. Yes, I think it's challenging. I don't want to make any bet about who's going to win, but I think it's also challenging.
Why did you say that you don't like the expression quantum locality?
No, locality I like. I don't like realism. This thing. I think, in my opinion, if you give to say person with no scientific education all these locality realism explanations, this person will not understand. And I believe you explain it in the way I was telling you, like, okay, things happen and they are not causally connected, and you have to provide in the CHSH with plus and times +1, okay? These people will understand and will bet money. Why did you give the EPR paper with locality and realism? You will say, okay, go, I don't understand anything about what you're telling me. This is more or less what I wanted to say. No, locality, yes, I like. I think locality, I prefer to think about causality, okay? When you say locality, what I'm saying is that what I do here is not causally affected by what happens there, because we are not all causes take some time to travel, okay? We are not all connected. That's why I prefer, from locality and realism, I prefer causality and determinism, which is more or less the same, but I prefer to phrase it. You may not like it, okay? But
Can I ask a follow-up? Yes, thanks. But would you agree with saying that what solved the issue of apparently infinite range communication is the fact that you need communication which needs to be transmitted classically, or is
well, I think causes propagate at finite speed. I would say this is what we are not infinitely connected, so causes propagate at finite speed. It can be the speed of light, but usually now it's very integrated on us that causes propagate with finite speed. And this is all what I need. Because then I can put arrows. Otherwise, arrows would be everywhere, no? If there was infinite speed. So I think I start by this assumption. Causes will propagate with finite speed. Then I can enforce experiments in which I can put arrows, if I have some confidence about the arrows, and then I can run the Bell test. If you want also, there is still an explanation which is always possible, which is superdeterminism. Everything was written in the Big Bang. Okay, this is also a possible explanation because it's something that people maybe will spend some time on that. And the cause is crucial for the Bell test. The Bell test only makes sense because you have this has to be true for the Bell inequality to hold. Okay, so otherwise it doesn't hold. And now when you plot this, you see this has no arrows. It happens with no arrows. In the Big Bang, there's an arrow here telling how to behave, okay? And this arrow can also go there. So this is an assumption, okay? I mean, there is always explanation, the Big Bang, everything was defined, even what I'm saying now, okay? And in the Bell test, usually when we do that is that we choose the random, you know about Bell test, we choose the random input and then we produce the result. But there is a lot of assumptions there. You say when the event starts and when the event ends. And this is crucial for you to be sure that information cannot go to the other place. So where does the measurement output, when is the measurement output produced? Okay, you see the photon goes to the detector, it creates a sequence of current of electrons, and then you observe with your eyes. You put a cat somewhere there, okay? So there are assumptions, but we tend to believe that we can design an experiment in which these causes describe the experiment and then identify the cause. But there is a lot of if in this sense.
Thank you. Do you have some opinion about this idea of, let's say, superdeterminism? So why we should exclude this or not?
Well, yes, I have an opinion, okay, I don't like it, but I mean, let's say, we are scientists, okay? In science, we need statements that we can falsify. Otherwise, I would say it's not a scientific statement. Superdeterminism cannot be falsified. So for me, it's something that is not in science, it's something different, okay? Because I can never assume that what I'm saying now and what we haven't was written. So this is unfalsifiable, hence it's not scientific. So this is my first opinion. Yeah, this is my opinion.
We started with ping pong balls and we reached God and so well, during this talk we've seen that we can break, for example, Bell inequalities with a maximal entangled state such as Bell states. Is there any study on what is the minimum amount of entanglement that you need to break them, and if so, can the violation of Bell inequalities be used as an experimental alternative for solving the separability problem to entanglement indices, for example?
Yes, okay, it's hard to answer all these questions. So yes, there are some studies, but there are also many unknowns. So we know that every Q state violates Bell inequality. We also know there are mixed states that are entangled that don't violate Bell inequality. Okay. And for instance, something that was one of my obsessions was I wanted to have a quantum information theory based only on Bell inequalities rather than entanglement theory, because I find it's really where quantum physics becomes different from classical physics, and this is the device independent approach that was mentioned before that we are going to give you more details, okay? But this sort of Bell-based quantum information theory, I would say, is the device-independent approach to quantum information theory, and this is what we have been doing in my group because I like so much the result that I want to do an information theory based on these things. It has also practical advantages, and for instance, a Bell inequality in this language is a device-independent entanglement witness. I cannot tell you more, but yes, there are things in the directions that you are saying.
It's quicker.
So my question is more about the quantum industry that you mentioned towards the end of the speech. Because just now we've said that most of the technology which is based on quantum still hasn't achieved what we hope that it achieves. So I was wondering, other than, of course, academia, is there such a thing as quantum industry, and what can a person do in a quantum industry, like what is being done?
Okay, so well, I mean, I will say something. To me, it's somehow a triviality. It always was that information technologies will attain the quantum world, and we will have to deal with quantum effects. Okay, so I think information devices are becoming smaller and smaller, and we're reaching the atomic scale. And I don't see why they will say, "Oh, we stop here, and we are not going to use quantum effects." For me, this is like it will happen, no matter how. Maybe not in the way you can see it now, okay? But this is like for me, if you were my son, I would say, go for it because it will happen. Now, how we don't know, okay? Maybe not in this way. There are also, and in this picture that I showed, For instance, there are things that also are going to happen. All the engineering and control of quantum devices like cryogenics, fast electronics, all these things they also are going to happen. They're going to do this, okay? Now about computers or quantum cryptography, perhaps the prospects are less clear. If you ask my personal opinion, I think they will happen as well. Okay, so I think the forest there, prospects are promising, still with some unknowns. And okay, for young people, why do you care so much about the long term? You will learn so many things that they will be of use in a way or another. So I'm not worried about this. I'm not sure if I'm answering your question, but it's not.